What happens to the flow of thermal energy when birds fluff their feathers in cold weather? If you've ever seen a bird like a pigeon outside, it's always fluffing its feathers. Why do they fluff their feathers? And how is this related to why cotton's ability to absorb a lot of water makes wet cotton clothing dangerous in winter? Well, when a bird fluffs its feathers, it's putting air in between each of those feathers. It's like if you have a big, um, puffy winter coat. It has maybe some cotton batting inside, like some cotton or some other synthetic substance inside it. Why does it have to be puffy? Why does that make it warmer? It's because that that creates air pockets, or in some substances it might not be air pockets, it might be actually empty space in between the strands of, in this case, strands of cotton, or in between the feathers of a bird. So the fluffed feathers, they trap the air and produce better thermal insulation. Cotton clothing might trap air and insulate well, but if those spaces become filled with water, like if you're wearing a cotton t-shirt, not a copper t-shirt, if you're wearing a cotton t-shirt and it gets soaking wet, you get caught in the rain, or I don't know, get in a water fight or whatever. You get caught in the rain and your cotton t-shirt gets soaked. Well, then the why is that so cold? It's like you want to remove the cold cotton because it's colder than just not having it on at all. And that's because the spaces that are designed to trap air are filled with water, and the water conducts heat away from your body instead of insulating your body. So that cold cotton clothing can actually do the opposite of what it's designed to do, and it can conduct heat rather than insulating it. So finally, let's think about the cube of shuttle material that we saw at the beginning of the lesson. We've seen this video a few times, and the technician put it in an oven. It got super, super hot. The sides glowed yellow with thermal energy, and the corners, the edges, were darker and cool enough to touch. What the differences in color? What information does this give you about how the material transfers thermal energy within the material into the environment? Well, the dark sections, the corners that have turned dark, they're no longer glowing hot. They've cooled to a point where they're not as hot as the flat sides. The corners and the edges, why do they do this? Well, they have the greatest ratio of surface area to underlying material. So again, we're coming back to the surface area to volume ratio. So the surface area at the edges and the corners is is greater when compared to the amount of material underneath it than it is on the flat sides. Right in the middle of the side of a cube, there's a whole cube underneath. Let's say a cubic cent or a square centimeter of the surface. There's the whole cube behind that. If you look at a square centimeter of the corner, well, first of all, a square centimeter of the corner has three sides to it, so it has a lot more surface area, and it doesn't have as much cube behind it to retain the heat. So the surface area allows the heat to radiate and escape, and the mass inside it uh, is what retains the heat. So that's why there's less contact with the air on the flat glowing sides and more material below the surface, and so the sides are still glowing hot. So what information does this give you? What evidence does this give you? Well, the glowing colors are the evidence. The glowing yellow, you can see the gradient of colors changing from the flat sides to the corners. That's evidence. And then um, the information about how this transfers thermal energy is that this evidence shows you that the corners are cooling off faster than the flat sides, especially in the middle of those sides.